Hi, welcome back everyone. This is the next session starting now. We're going to talk about heat exchange coefficient calibration during thermal treatment, and our presenter today are Khalil Traidi from SafranTech and Nina Muelo from Data Advance. So I have first to apologize Mr. Traidi because he has a last minute change in his agenda, and unfortunately will not be able to attend this conference. The paper has been prepared jointly with Khalil and Nina, so no problem. We can take over and fully handle the presentation. So with this, I would like to give the floor to Nina Muelo, who's application engineer working at Data Advance. So Nina, the floor is yours.
Thank you, Laurent. Good afternoon, everyone, and thank you for joining this conference. So like Laurent introduced, I will speak today about identification and calibration of heat exchange coefficient during thermal treatment. I'll start with a presentation of the company with whom we worked, which is SafranTech, more precisely. I then introduce a bit the calibration problem and state a bit the issues we had to solve. Then I'll move to the proposed approach and the methodology we put in place to solve this calibration problem. And I'll finish with a conclusion and some perspective of evolution. So to start with, this project has been built with Safran. Safran is an international group, a French international group, aiming at producing equipment, propulsion, and electronics devices for both aerospace and defense, so both military and civil applications. And inside this company, the SafranTech department is the, let's say, research and development part of the group. So Khalil, with whom I worked on this project, is part of this SafranTech department. For each part of the power transmission equipment that they are manufacturing, thermal treatment is performed with the aim to improve mechanical performances and surface resistance. So we have a picture here of this kind of process. And during those heat treatments, you have several steps which are shown here. So you can see heating phase, then stabilization, cooling down again, heating. So this is a long process, and this entire treatment can be a source of distortions and changes in the shape of the parts. So you have an example here with like times 50 of scale. So everything is improved, bigger. And so to prevent those kind of changes and to anticipate any failure, we are using simulation to prevent and let's say model this kind of behavior. But the problem is that to ensure accurate estimations with the simulation, we are relying on some boundary conditions that must be evaluated first. So those boundary conditions are, for example, heat exchange coefficients, heat transfer coefficients. So we call it HTC. And those HTC must be calibrated because they cannot be measured. So they are calibrated using temperature measurements. So you have here an example of an instrumentation of a part with some sensors on the parts used to measure the temperature during this thermal treatment. And based on the temperature evolution, the goal is then to identify those heat transfer coefficients. So because of this process with the simulation and the identification is a very long process, SafranTech was then relying on P7 tool, the desktop version, to help in this analysis and to speed up the process. So here is our calibration problem. We want to identify those heat exchange coefficients of a specific part based on experimental measurements of the temperature during cooling. So you have a graph here of this temperature measurements at some specific timestamps during a cooling phase. We have been worked on a part with 2 sensors, so that's why you have 2 curves. You see that those curves are not behaving in the same way. Okay, sometimes a curve has a descending variation, where the other one has more stable or more flat variations, let's say. So those 2 sensors were placed on the superior and inferior parts of the piece. Okay, and the goal is to get this kind of curve, which defines the HTC depending on the temperature evolution. Something important here is that this HTC curve cannot be evaluated from the physics. Here we are really based on the industrial conditions of the heating process. Okay, if I go back on my previous slide, we are really taking into account this kind of conditions here, with the environments also playing a role and so on. That's what makes also a bit more complex the use case. So to identify those heat exchange coefficients, we are relying on Forge simulations, okay, to match with the experimental data. And something important is that this kind of process of identification can take several months if it's done by hand. Why so? Because the engineer has to match the temperature evolution, so the temperature graph at each timestamp. So at several, let's say, steps of the process, you have to ensure good calibration. And you have to know that one simulation with Forge takes around 2 hours. So imagine that you have to repeat this process to ensure the good calibration, which takes 2 hours for each simulation, and then do that for each of the timestamps. You can imagine that it's a very long process. So we have been facing several questions, okay, with the goal to identify the HTC. So this is our main goal. But the first question was how to get the information about the heat transfer coefficient on the experimental set. So this is with matching with this temperature information, actually. Then we went to a question on how to split the simulation time to have the most accurate identification, knowing that the experimental temperature evolution, so the curve variation, this means that we have to select actually some important parts of this temperature evolution in order to build something quite accurate. You will see that we have some most interesting parts that we want to study more, and some flat area where we can avoid some computations. So we put in place a method to select this simulation time split. And the last, let's say, challenge was to integrate Forge computations in P7. So I will explain all of that now. The proposed approach was first then to integrate these Forge simulations through file management. George presented before that P7 is able to run a program, an external program on P7 just using information from input file and output file and some commands in the middle. That's exactly what we did with this very generic integration of external softwares. We then also decided to use several splitting time techniques that are to be compared by the user. So then by going through all those time steps one by one, so decided by this splitting time technique, for each time step, we put in place an optimization campaign where the objective was to reduce the difference in temperature between the measured data and the simulation data. And the variable of these problems were these HTC values. So all of that was also done using Forge. And in the end of this entire process, P7 is able to return a report with some curves and data automatically generated. to give a feedback to the user. So all of that was implemented in this workflow that may seem a bit complex, but I will explain it step by step to make it more clear. So let's start with the beginning. So the block here on top. This block here has the simple goal of integrating Forge simulations. So it's just like preparation of files. Okay, Forge needs some specific commands to run. It needs some files to be placed at very specific folders and so on. So this is what is done here. Just a reminder, this composite block is actually embedding a sub workflow. So this is what is shown here. So this is just like, let's say, administration of all the files. Okay, once the project is ready, we go to the time split part. So this is where you have three different options. You recover here the curve of temperature evolution. And depending on the method you select and some other parameters, you have access to first this constant split method. So the user here has just to select one, let's say, interval between 2 points. So let's say, for example, we select 4 seconds. Then the curve here of temperature, so this experimental curve, will be split into several parts separated by 4 seconds each, okay, to have a first database to be compared then with the simulation. The second option is this smart split. Here in that case, the criterion is more about the derivative, okay, so the gradient information. The higher the gradient is, the more point you had on the curve. So it enables to get more information where you have more variations, and where the curve is flat, like here, you see we need less information, so that's why we will run less simulations. And it enables saving time on those least significant parts. The last one, the cutted split, is just a mix of both. Between an interval that the user chooses, you have this constant split, and outside of this interval, you have this smart split selection. So it enables everything to be very customizable and adjusted by the user. So then it's the role of the user and the researchers to play with those. Once you've selected a time technique here in this part with the specific criterion, you enter a first loop. So this is a very large loop where the map here will iterate on each of those points. Okay, so each of those time steps. At each time step, you prepare a bit again some files, like we did here, to change this timing information. And then you enter an optimization phase. So I will explain it just after. This optimization is where you want to reduce the, let's say, the error between the measured temperature and simulated results. So you do this for all your time steps. At each time step, P7 saves the information of the optimal HTC, okay, and it iterates again the next one and so on. Then let's detail a bit this DSE block, so the optimization process. DSE stands for Design Space Exploration. So it's the block that is managing this optimization campaign of reducing the difference in temperature by playing on those HTC values. So alpha is another name for the HTC values here. You see it's our variable. And in the responses, we want to minimize this error. Okay, so the process is that this DSE block will provide some HTC values to be played by Forge. Okay, Forge proceeds with this simulation using also GL-pre as preprocessor. And the program block is then used to launch those programs. Once Forge provides the end of the simulation, it will output the obtained temperature, that is a post-processing here, with this comparison with the measured temperature at the same time step. Okay, and this difference gives an error to be sent back to the DSE block. So you enter this kind of loop, and with the technique of surrogate-based optimization, which has been smartly selected with our smart selection algorithms, this will enable faster optimization, so faster reduction in this error. So in the end, faster calibration of what is the expected HTC on the measured values. Okay, and then in the end, after going through all the steps and having an optimization for all the temperature parts, P7 is able to produce a report. So you have a picture here of what is produced. Here you have both curves of the HTC we wanted to calibrate. So this is just the measured data. And you have in gray all the points that were selected from the time split. So we can guess here that we had this kind of smart split selection, because for the flat areas, we don't have any points. Here you have a result of the error computed at each time step that was optimized. So this is the minimal error P7 can provide. And here you see actually this matching between simulation and experiments. So we took here the green curve, and you see that P7 with the green curve on this part is actually very close to what is done in the experiments. You have maybe some improvement to make here, but you can also see that we have less points in this part, so that may be linked. So maybe the user can just tune it with adding more simulations here. And in the end, you have this HTC versus time curves that we wanted to get for both sensors. So to conclude, we went through this fully automated approach to allow faster identification of this HTC, so those coefficients. The entire process takes less than 6 hours. So you see here the benefits compared to a month of works if it's done by hand. The user also have access to 3 time splitting techniques, which he can explore and change some options. So change the intervals, the gradient criterion, and so on. And in the end, reports are generated in the form of HTML files. So this allows people to just send those files elsewhere outside of P7, and it allows them to have like decision-making on another department or at managing level, for example, without the need of using P7. So the global conclusion is that we have a reduced cost, complexity, and time. And this is then to be applied to other industrial parts now. Thank you very much. And do not hesitate if you have any question.
Yeah, thank you, Nina, for your clear presentation. You finished it just right on time, so I guess I have time to go through the Q&A section and pick 1 or 2 questions for you.
Great.
So I have one here. The first one would be, is the workflow made for only one specific part, or can we use it to calibrate a new one, like on a different object? So basically, how generic is the workflow?
Yes, sure. Well, we first tried with sorry, I'm going back on the parts. We first tried with a very dummy object, which is actually this one. So it's like just a box, just as a proof of concept of the workflow. But then we made the workflow such that you have general parameters on the run section of the workflow to be easily changed. So the user can just change the reference files for measurements and simulation and apply the same process for any other part. And that's actually what is doing right now with testing this process on a real part now.
Okay, thank you for your answer. So I think you are actually on the next session, so maybe I should free you. And thank you very much for your presentation. And please, everyone, move on to the next session presented by Nina again. And thank you. And also Joanne Garitzen from Dresden University of Technology. The title of the presentation is Efficient Optimization of Material Properties Based on Experimental Data. So please, everyone, move on to the next session. Thank you.